Okay, so this is where we are going to start up today. Part of being successful in this class is not just doing like the math and taking the notes, is I try to give you, hints and ways to recognize problems and what's going on in them. So writing those down is going to be kind of important in terms of being successful in this class. I try to tell you how to identify what type of problem is and where to go, because it's not that the math is so hard, it's just knowing what to do with the numbers can be challenging. So let's look at this problem right here. I give you silver nitrate and I'm mixing it with sodium chloride. So two things are happening. One, dilution is happening. How do I know? I'm taking two solutions and I'm mixing them together. So not only is dilution happening, a chemical reaction is also going to happen. Okay, so we're going to find out what the concentration of all ions present at the end of the reaction and how much precipitate is produced. So let's go ahead and write out the reaction. Silver nitrate and sodium chloride. So silver nitrate plus sodium chloride is going to make sodium nitrate and silver chloride. So this is aqueous because alkali metals are always soluble. So by default, silver chloride is your precipitate, and then your reactants were aqueous. They were in solution. Everything is 1 to 1 to 1. Now, you can take and break everything apart that's aqueous and then write the net ionic, but can anyone tell me, I'm not going to do that right now for the sake of time, can anybody tell me just by glancing at this if you can figure out who the spectator ions are?
Na and NO3.
Beautiful. Who was that?
Skylar.
Skylar, thank you. Okay, so sodium ion concentration and nitrate ion concentration, we're going to know very early on. We're going to know after we did the dilution their concentrations because they do not participate in the reaction. It's just the silver and the chloride making silver chloride. The sodium and the nitrate are just floating around minding their own business. So now that I have the reaction, I've already identified my spectator ions, I'm going to do the dilution. So the dilution occurs when you mix them, but before they react. So you need to do the dilution for silver nitrate, and then you need to do the dilution for sodium chloride. So let's go look up. Silver nitrate is 0.4 molar. You have 50 milliliters of it. When you mix it, you're going to have 100 milliliters of stuff. So this is M1V1. M2 is your new molarity, your diluted molarity, and V2 should be 100 for both of them. So, oops. Here we go. So silver nitrate, let's see, I'll do it down here. 0.4 molar. I have 50 milliliters of it. New molarity. And the final volume is 100 milliliters. So you divide both sides by 100 milliliters to get the new molarity. And you end up with 0.200 molar silver nitrate. So it was 0.4 molar, but because you mixed it with someone else, it dropped down to 0.2 molar. Okay, and then we need to do this again, but for sodium chloride. I think, if I'm not mistaken, the sodium chloride was like this. I think it was 0.3 molar. And we had 50 milliliters of it. Has a new molarity, and again, final volume is 100. So divide both sides by 100 milliliters. And you end up with 0.150 molar sodium chloride. Now, you know the sodium and the nitrate right now. If it's 0.15 molar sodium chloride, it's 0.15 molar sodium because there's one sodium ion in sodium chloride. If it's 0.2 molar silver nitrate, it's 0.2 molar nitrate because there's one nitrate in silver nitrate. So I know my sodium and my nitrate ion concentration off the bat. questions so far? So now I need to react them. And I had a really great question last period. There seemed to be some confusion because I am doing limiting reactant problems with molarity and not moles, and that seems to have thrown a few kids off of understanding why I'm using molarity instead of moles. There is no reason that you cannot do moles. You can take this molarity and multiply by the volume to get moles here, and you can take this molarity and the volume and get moles here, and then do a limiting reactant problem with mole-to-mole ratios, and then you can find out how many moles you have at the end. But then you have to redivide, because I don't ask for moles in this problem, I ask for molarity. So you have to redivide by the number that you multiplied by to begin with. So what I'm doing is I already did that right here, so I'm skipping that step. I'm using molarity because both of these guys' volumes are the same now. They're both in the same container. So I'm able to use their molarities in replace of moles. You would be multiplying by volume and then dividing by volume, which in essence does nothing. So I'm just letting myself use molarity here, okay? So this is 0.2 molar, and this is 0.150 molar. Now, so we've done the dilution. Now what kind of problem is it? You have amounts of both reactants. What kind of problem is it?
Limiting reactant.
Limiting reactant. Now what's really nice is these guys react in a 1-to-1 ratio, so whoever is smaller is my limiting because they're reacting in a perfect 1-to-1 ratio. So that's going to be sodium chloride. So how much of the sodium chloride does it change? So this is initial, how much we have. This is how much it's changing, meaning how much it's losing. How much am I going to lose of the limiting? All of it. That's the point of it being the limiting reactant. So at the end, I shouldn't have any of it. At the end, I should have none of it. So if I have 0 molar sodium chloride, the chloride ion then, and it's not the sodium, remember, is 0 molar. 0 chloride. Now, they're reacting in a 1-to-1 ratio right here. So whatever this number is, this is the same number. I'm going to lose this much here because they're reacting in a 1-to-1 ratio. So I end with 0.005, or no, is it 0.005? Why does my brain not work? I have too many zeros. Okay, so 0.05 molar AgNO3, that belongs to this guy. 0.2 minus 0.15 of it react, so this is excess. So that's how much silver ion I have. Where can I go with my silver? Let me just erase some stuff down here. So my silver ion is 0.0500 molar after it reacts. Okay. So we answered all the questions so far, but they also ask you for the mass of the precipitate. That's this guy. Any suggestions of how I could do that? How do I find out about this guy? First of all, who do I use? Do I use the sodium chloride or the silver nitrate to find out about silver chloride? Which reactant do I use? Sodium chloride, the limiting, very good. So I'm going to use this guy's number. So 0.150 moles per liter. That's what big M means. How many liters are there? 100 milliliters, which is 0.1. I gotta get this out of the way, sorry. So this gives me 0.015 moles of sodium chloride. For every 1 mole of sodium chloride that react, 1 mole of silver chloride is produced. And we can go look on the molar mass. 1 mole of silver chloride has a molar mass. Let's see. Okay. All right, let's move on. So FRQ 2006B, number 8, part D, says use chemical and physical principles to account for each of the following. So the redness and itching of the skin caused by anbites, which is methanoic acid, can be relieved by a paste made from water and baking soda. Remember, baking soda is sodium bicarbonate. You want to answer why it's relieved. Well, this is going to be an acid-base neutralization reaction, so the baking soda neutralizes the acid, which is why you would find relief from it. But they also asked you to include a chemical equation, so let's do that. So methanoic acid is an organic acid. It actually looks like this. Okay, so this right here is the acidic hydrogen. That's the acidic part of it. It's the one that's attached to the oxygen. So we have HCO2H plus sodium bicarbonate, NaHCO3, and we should get how many products?
3.
3, thank you. Okay, so we're gonna get salt, NaHCO2, this part, because this is the acidic hydrogen, plus water, plus carbon dioxide. Okay, and then again, you would go on to explain that the reason that you'd find relief is that this is a base and the base neutralizes the acid, and so it would feel better. Questions about this FRQ? Okay, let's try another one. So concentrated sulfuric acid, and they give you a whole bunch of information about it. And part A asks you to calculate the volume of concentrated acid required to prepare a volume and a molarity of diluted acid. So this first part A is just dilution. This is M1V1, M2V2. So what's the molarity? I have 18.4 molar. What volume? I don't know. That's what I'm solving for. What's the new molarity they want? 5.2 molar. How much do they want of it? 1 liter. So you take and you divide both sides by 18.4 molar. And you get 0.283 liters, which would be 283 milliliters. Questions? Okay, so that was A. Now we're going to do C. It says calculate the volume of 5.2 molar sulfuric acid that can be completely neutralized by sodium bicarbonate. So this is a chemical reaction now. This isn't a dilution. Okay, now, is it a limiting reactant problem? Ugh, it's ugly. This is not a limiting reactant problem. I have mass of this guy, so I do know the moles of this guy. I have the molar of the sulfuric acid, but I don't know how much of it, right? If I need molarity and volume to get me moles of sulfuric acid, and I don't know the volume. That's what you're trying to find out. So this isn't a limiting reactant problem. It's just a stoichiometry problem. So salt, water, carbon dioxide again. Then we have to balance two of these guys. Now I have 4 hydrogens, so I need a 2 here. I have 2 carbons, so I need a 2 here. That gives me 6, 4, 10 oxygens. 4 plus 2 plus 4 is 10, so we're good. So what do? Well, if I know molarity equals moles per liter, I know molarity. I want to know volume. That's what I'm questioning. So if I could somehow get moles of sulfuric acid, then I could figure out the volume. Remember, if you rearrange this, liters equals moles over molarity. The liters has to come up and the molarity goes on the bottom. So I do have a way to get there, right? 10.5 grams of sodium bicarbonate. You can turn grams into moles. I think it's 84.01. Oh, I don't remember. It is 84.01. Oh, it's not letting me go back. Why is this happening? Sorry guys, my thing is like frozen. It turns it off. Okay, so let's see. We have to do mole to mole ratios. For every 2 moles of sodium bicarbonate that react, 1 mole of H2SO4 reacts. It is a 2 to 1 ratio. So now I have moles of H2SO4. Well, if I have moles and I have molarity, I can find volume. So my moles is 10.5 divided by 84.01 divided by 2. My moles are, so volume equals 0.06249-ish moles over 5.20 moles per liter. My moles cancel. I'm left with liters. So it's 0.012 liters, which would be 12 milliliters. Grams to moles to moles, back into the molarity equation. Any questions so far? Okay. All right. An unknown sample of a monoprotic means 1 hydrogen acid, was dissolved in water, and then they neutralize it with sodium hydroxide, and they want to know the molar mass of the acid. So you're so used to being given molar mass that for some reason, kids don't realize that they can calculate molar mass without knowing the identity of the substance. So that would be done like this. Molar mass is defined as grams over moles. So if you know grams and you know moles, you can take your grams and divide by your moles and you can get molar mass. So I'm already like halfway there. I have the gram of the sample. So I don't have to worry about that part. I have it. It's given in the problem. 3.664 grams of the sample. So really what I need to find out is I need to find about the moles of the acid. So monoprotic means one hydrogen. So I'm going to just say this is like HA. If there's one hydrogen, hydrogen is +1, so whoever it's hooked up with is -1. Maybe it's HCl, maybe it's HBr, maybe it's HNO3, but it's definitely not like H2SO4 because that would be a diprotic. So monoprotic means just one hydrogen. So you can write out a generic chemical reaction of the acid reacting with sodium hydroxide to make salt, Na, and then some other thing, and water. And they do react in a 1-to-1 ratio. So if I know the molarity and the volume of base, I can get the moles of base, and then I can do mole ratios to get the moles of the acid. So let's do that. Molarity times volume is moles. So 0.1578 moles per liter times 0.02027 liters is going to give me my moles of base required to neutralize the acid, 0.02027. Oops, 0.1578 times 0.02027. So this ends up being like 0.003131986 blah blah blah, just keep your whole number in the calculator, moles of NaOH. And for every 1 mole of NaOH that react, 1 mole of the acid react. So it's the same number for the acid. So this number, now I have moles of acid. So it goes here. So 3.664 divided by 0.0031986. And you end up with, this is 4 digits, this is 4 digits, this is 4 digits. So your answer is 4 digits. A really big number, 1,145 grams per mole. And you go, that seems just like way too big. Well, likely, and we don't know for sure, but this might be an organic acid. Remember, organic acids involve carbons, and carbons have the potential to make ridiculously long chains. And so this could be like a heavy organic acid, which is why you would see a number so big right here. It's definitely not like HCl or HBr. Those are like what? HCl is like 36 grams per mole. So this is definitely not one of those. Any questions? Okay. All right, so we have done all types of reactions. So we've done precipitate reactions where we produce a solid. We've done acid-base neutralization reactions. We have a couple that we have to memorize, like the carbonates and bicarbonates with an acid give us salt, water, and carbon dioxide. The copper and the nitric acid gave us salt, water, and nitrogen dioxide. We've also worked with synthesis or decomposition, and now we're going to work with what are called redox reactions or oxidation reduction reactions. This is the last topic in this chapter. You actually have done redox reactions already without knowing it. You did not know they were redox. You will now, but you have done redox reactions without knowing them. So let's talk a little bit about it. So assigning oxidation numbers is how you keep track of like charge in a compound. So all elements oxidation numbers are 0. So like all of these guys oxidation states would be 0. And then for neutral molecules, all of the elements have to add up to 0 because there's no charge. Now if there is a charge, all the elements have to add up to what the charge is. For the sake of this class, oxygen is almost always -2. It's super electronegative, which we'll talk about in a second. But there is a time where it is -1, and that's when it's in a peroxide. So peroxide is called O2 2 minus. It kind of looks like that mercury one. There's each oxygen is -1 to give a total of -2, and two of them. This is a peroxide, and it's the rare instant that oxygen is not -2. This also happens with hydrogen ions. Hydrogen ions are almost always +1. But when they're with a metal, the metal gets the positive charge, and that leaves the hydrogen being -1. Those are called metal hydrides, and they're not super common, but they do happen for those two. So in order to figure out who gets to be the negative charge, you have to do something called electronegativity. And electronegativity is how attracted an element is to an electron. The more attracted an element is to an electron, the more chance it's going to have of having the negative charge. Generally, in most compounds, the first element that is written is the positive one, and the next one are the negative ones. But this isn't always true. So ammonia is a perfect example. If you look at this electronegativity chart, the most electronegative element on the periodic table is fluorine. It is the most electronegative element. Right after fluorine, it's oxygen, and then it's nitrogen. Those are the three most electronegative elements on the periodic table. So the closer you are to those elements, the more electronegative you are, meaning the more chance you're going to be able to attract electrons and become negatively, have like a negative oxidation state. The only exception to that is our noble gas family. They don't have attraction to electrons, right? They're stable, they have full stable shells, so they don't have any electronegativity because they don't want to attract electrons. They're happy just the way they are, and they're stable, and so we don't count them in this trend, okay, for electronegativity. So, oops. These types of reactions, oxidation reduction, also known as redox reactions, are reactions you've already done. You just didn't know that they were redox reactions. So synthesis and combination reactions can be redox reactions. Decomposition can be redox reactions. Single replacement can be redox reactions. Combustion reactions are redox reactions. Generally, our double replacement and acid-base problems are not redox, and so let me show you why. So we need to assign oxidation states to every single element in the reaction, or ion, I guess we could do. So this is a double replacement reaction. So you go, okay, well, what's magnesium? Magnesium's +2. What's chlorine? -1. What's potassium? +1. What's nitrate? -1. What's magnesium? +2. What's nitrate? -1. What's potassium? +1. What's chloride? -1. In order to be redox, things have to change oxidation states. The magnesium is still +2. The chlorides are still -1. The potassium is still +1. The nitrate is still -1. None of these changed oxidation states, so it can't be a redox reaction. The same is true with this acid-base neutralization. Hydrogen's +1, chlorine's -1, sodium's +1, hydroxide's -1, hydrogen's +1, hydroxide's -1, sodium's +1, chlorine's -1. So this is not a redox reaction. So let's assign, this is combustion. This is the combustion of methane. So let's assign oxidation numbers to every element. Hydrogen is +1 unless it's with a metal. So that means +1 times 4 is +4, so the carbon is -4. This is neutral elemental oxygen, no charge. Oxygen is -2 times 2 is -4, so the carbon has to be +4. Oxygen is -2. Hydrogen is +1 times 2 is +2. That cancels out the -2. So look at the carbon went from -4 to +4, and the oxygen went from 0 to -2 in both instances. So this is a redox reaction because oxidation numbers changed. This is -4, now it's +4. Question so far? Okay, let's write out this problem. Sodium reacts with chlorine. Sodium reacts with chlorine. What would you guess that this makes?
Salt.
It does make salt. NaCl. And then you can balance. So let's look. Sodium right here is an element, so it's 0. Chlorine is pure chlorine, so it's 0. Sodium right here is +1. Chlorine is -1. So sodium changed and chlorine changed. So this is a redox reaction. It's also a synthesis reaction, but it's also a redox reaction. Okay, so sometimes the reactant can get both reduced and oxidized at the same time. That is possible. It's called disproportionation. And in order to be redox, you have to have both oxidation and reduction occurring. You can't have one without the other. They go hand in hand. The way that I teach kids to remember what oxidation means and what losing is these mnemonic devices. So Leo says GR, losing electrons is oxidation. Gaining electrons is reduction. So that's one way to remember it. You have to know what's being oxidized and what's being reduced. The other way, this is just a different way, oxidation is losing, reduction is gaining. So either one you choose, oil rig or Leo says GR, just whatever one you choose is fine with me, but definitely remember one of them so you know how to identify who's oxidized and who's reduced. So if we go back and look at this reaction, the 2Na plus Cl2 makes 2NaCl. So 0, 0, +1, -1. The sodium went from 0 to +1, which means it lost 1 electron. Losing electrons is oxidation. So this is your oxidized species. By default, that makes this guy your reduced species, but let's talk about why it's reduced. The chlorine gains 1 electron to become -1. Gaining electrons is reduction. So this is your oxidized species and this is your reduced species. Questions? Okay. What's interesting is that if you're a species that is reduced, you're called the oxidizing agent. And if you're the species that's oxidized, you're called the reducing agent. The reason that is because what the substances are doing is they're transferring electrons. One thing is losing them and the other one's taking them. So the guy that loses the electrons is oxidized, but it's causing the other species to be reduced, which is why they call it the reducing agent. And then, of course, the reverse is true. The substance that's being reduced is gaining electrons. Well, it's gaining electrons because it's oxidizing or taking them away from a different substance. So it's called the oxidizing agent. It causes the other thing to become oxidized. Okay, and we'll do a bunch of practice with this. I'm not going to read this for you. I'm going to go over this. We're going to do this. It's not going to really make sense until we start practicing. So these slides, you can kind of look back for reference, but we're going to start balancing redox reactions, and there's a method of doing it, and you do it the same way every single time. So it's kind of like puzzle solving, and we'll be practicing. It will have, I think, 3 of practices, and then we'll be done. So a hint that you're balancing a redox reaction is they give you a net ionic, or they give you a reaction that shows a bunch of charges in there. So I think I did this. Okay, so this is Ag to Ag plus and Mn, what is it, 2 plus? Okay, so we're going to go through these step by step. Step 1, you break these down into what are called half reactions. So you find the substances that look alike. So like these guys look alike, and these guys look alike, and you write the reaction with just those things in them. So silver going to silver ion. This is a half reaction. And then permanganate going to manganese ion. This is another half reaction. Okay, so that's the first step. Write out half reactions. Second step, you balance all elements other than oxygens and hydrogens. So there's one silver here, one silver here. I'm good. There's one manganese here, there's one manganese here. I'm good. Okay, the next thing you balance are oxygens. So it will always go in this order. The next thing you balance are oxygens. This guy does not have any oxygens, so I don't need to balance with oxygens. This guy does though. This guy has 4 oxygens. I balance oxygens with waters. So I'll add 4 waters because that will give me 4 oxygens. And the reason that I'm allowed to do this is because all of these are done in an aqueous environment. Aqueous means there's water present. So that is why I'm allowed to add water molecules for oxygens. So adding the water molecule in turn gave me hydrogen ions. So that's what you balance next. And you do it doing 8 hydrogen ions. And you go, well, why can I do that? Well, if you look back at this slide, it says this is being done in an acidic environment, meaning there's hydrogen ions floating around in there. That's what it means to be acidic. H plus ions are what makes something acidic. So that's why I'm allowed to just add hydrogen ions to the other side. Okay. Now, once all elements are balanced, you need to balance the charge, and we balance the charge with electrons. So the charge over here is 0. The charge over here is +1. So I'm going to add 1 electron over here because +1 and -1 is 0. So now this side is 0 and this side is 0, and they match. Okay. Now, what is the charge over here? Well, this is +2. This is neutral, so it's +2 over here. What is the charge over here? Well, this is +8 -1 is +7. So these definitely don't match, and I need them to. So a hint is if you already know what side one of the electrons is on, if it's on like the product side, the electrons have to be on the reactant side of the other reaction because one thing is losing them and the other thing is taking them in or gaining them. So it's going to be electrons over here, but how many?
5.
5 electrons, because 5 negatives and 7 positives leave me with 2 extra positives, which now match this side. They're the same now. Once the electrons have been established, you need to force the electrons to match. It's kind of like law of conservation of mass. This guy can't spit out 1 electron and this guy take 5 electrons. You can't get 5 electrons from 1. So I have to take this first equation and I have to multiply it by 5 so that my electrons match. So now I end up with 5 silver makes 5 silver ion plus 5 electrons. So this goes away now. All right, now that my electrons match, here is the process. Anything on the opposite sides of the reaction arrow are subtractive. They cancel each other out. Anything on the same side of the reaction arrow gets added together. So 5 electrons on the left and 5 electrons on the right totally cancel out. That's it. Nothing else is the same. This is silver ion. It's not the same. So I'm going to just write out what's left over. I have 8 H pluses. I have MnO4 minus. I have 5 silver. Makes 5 silver ion. I'm combining both reactions. And Mn2 plus and 4 waters. So this is my balanced redox reaction. Holy moly. Any questions before we're going to do 2 more practices? Okay. Oh, I forgot. We were supposed to determine, sorry, we were supposed to determine who was reduced and who was oxidized. So reduction is the thing that takes in electrons. So look at the electrons go into this reaction. So the permanganate is the reduced species, and it's also your oxidizing agent. That means the silver, look at the silver lost, it got rid of, it lost electrons. So the silver is oxidized and it's called the reducing agent. It loses its electrons to give it to permanganate. They transfer their electrons. Okay, so let's try another one. Oh, so chloride, dichromate, chromium, and chlorine. So we're going to split these into half reactions. Oops, I gotta go back in. Chloride, dichromate, chromium. Okay, so you do the things that look alike. Ooh, my bad. So, ooh, don't chud. The chloride going to chlorine and the dichromate going to chromium ion. So these are my half reactions. So the first thing you do is you balance all elements other than oxygens and hydrogens. So in this case, look, I have 2 chlorines right here, so I have to put a 2 right here. Look, I have 2 chromiums right here, so I have to put a 2 right here. So all elements other than oxygens and hydrogens. Okay, the next thing I do is I balance oxygens. That's the next step. There's no oxygens in this top half reaction, so I'm not going to even do anything up there. There are down here though, there's 7 of them. So I balance oxygens by introducing water. 7 oxygens. That in turn gives me 14 hydrogens. Okay, and I get to do this because it's in an acidic environment, and that's what hydrogen ions represent. Okay, so the next thing, so all elements are balanced. The next thing you have to do is balance charge. So this is -2 right here. So I have to put -2, 2 electrons over here. This guy is losing electrons. Losing, it's getting rid of, losing electrons. So Cl- is my oxidized species, also known as the reducing agent, which by default makes the dichromate the reduced species, which makes it the oxidizing agent. So I need to balance charge down here. This charge is +6. 2 times 3 is 6, and this is 0, so it's +6. This charge over here is +14 -2, so +12. Now I need them to match. So what am I going to do? Well, I'm going to add 6 electrons over here because 6 negative charges will bring this +12 down to +6, and now the charges match. Any questions about that part? Okay, now that everything matches, I have to force the electrons to match. So this is 6 and this is 2. So I'm going to have to multiply this guy right here by 3 to get 6 electrons over here to match these 6 electrons over here. So that ends up leaving me with, I'm going to do a different color. 6 chloride ion makes 3 Cl2 ions plus 6 electrons. So Okay, now everything on opposite sides cancels. So I have 6 electrons on the left and 6 electrons on the right, so they cancel. And that's pretty much everything that's the same. So I got to write out what's left over. So I have 14 hydrogen ions. I have dichromate ion. I have 6 chloride ions. Those are all reactants. Okay, products. 2 chromium ions. 7 waters right here. And 3 Cl2s. Now everything should work out. So this is my balanced redox reaction. Everything should work out. Let's look at charge. This is plus 14. This is minus 2. So that's what? Plus 12. Minus 6. So that's plus 6. 2 times 3 is plus 6. 14 hydrogens. 14 hydrogens. 2 chromiums. 2 chromiums. 6 chlorines. 6 chlorines. Right? Everything matches. Questions? This tells you it's acidic. It has hydrogen ions floating around in there. Okay. Oh, I guess we have 2 more. So we have this one and then 1 more. So let's try this again. So I do recognize that there are hydrogen and waters in here, but right, H is +1, water's +1. So this is not the things that are changing. You want to do the half reactions based on the 2 things that are changing, which it looks like the chromium and the carbons are what are changing. So that's how you're going to split your half reactions, and you're going to ignore the hydrogens and the hydroxides. You just ignore them. You can fill them in later. I'm going to try to remember this. So dichromate to chromium and ethanol to carbon dioxide. So dichromate to chromium ion. It's 1/2 reaction. And then ethanol, C2H5OH, it's alcohol, to carbon dioxide. All right, first thing you do, balance all elements other than oxygen and hydrogen. So I see 2 chromiums right here, so I have to put a 2 here. Next thing you balance are oxygens, and you balance oxygens by introducing waters, 7H2O. So that's 7 waters. That gives me 14 hydrogens. Okay, now we have to balance charge. This is +6 right here. This is +14. Minus 2 is +12. So I'm going to need 6 electrons over here. Okay. So let's see, 2 carbons. So I need 2 carbons. The next thing we balance are oxygens. There's 4 oxygens over here and there's 1 right here. So I only need 3 waters because that will give me 3 oxygens plus this guy right here is a total of 4 oxygens. Now there's hydrogens everywhere. So there's 3 times 2 is 6, plus 5 more is 11, plus 1 more is 12. So there's 12 hydrogens I've got to add over here. Okay, now this side is neutral, 0 and 0. So I'm going to need this side to be neutral, and I will do that by adding 12 electrons. 12 positives and 12 negatives add up to 0. Question so far. Okay, now I need to force my electrons to match. This is 12 and this is 6. So I'm going to multiply that top equation by the number 2 because 6 times 2 is 12. You want the electrons to match. So I'll have 12 electrons. I'll have 28 hydrogen ions. I'll have 2 dichromates. I'll have 4 chromium ions and 14 waters. Question so far? Okay, so I'm going to get rid of this guy. Now, we need to reduce everything that can be reduced. So things on opposite sides are subtractive and things on the same side get added together. So 12 electrons on the left and 12 electrons on the right. So those cancel. Now, we actually have things on opposite sides of other substances this time. Look, I have 28 hydrogens on the reactant side, but I have 12 on the product side. So what do we do with these two numbers? Well, we subtract them. I'll lose all 12 right here, and 28 minus 12 leaves me with 16 hydrogens left over. So the same for the water. I have 3 waters over here and 14 on the opposite side. So I'll lose all 3, and 14 minus 3 is 11 waters left over. Now we can write out everything. So 16 hydrogen ions plus ethanol plus dichromate why is it doing that? Sorry. Makes 2 carbon dioxide right here, 4 chromium ions right here, and 11 waters. Okay, so if I go back to that reaction, I could fill those numbers in, right? This is, this is 16. I think this was 4. This was 11. Oh shoot, I forgot what they all were. 1 dichromate, or 2 dichromates, 2 carbon dioxides, 2 dichromates, 2 of these guys, and 2 carbon dioxides. So this is your balanced redox reaction. Whew, how are we feeling? Okay, so the next problem I'm going to do is not going to be an acidic problem. It's going to be a basic problem. Everybody listen. Listen, 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 listen. You are going to do this problem just like we've been doing our problems. I'm not going to have you change anything until the very, very end. You don't do anything until the very, very end. So I want you to balance this as if it's an acidic problem. So I want you to try. Now, I've done 3 examples with you. So hopefully you can try to do this a little bit on your own. I'm going to be working it out, but I want you to please try to do this at least a little bit independently. And then I'll show you what it being basic means in terms of the difference. But for now, I want you to balance it just like I've been showing you how to balance it. Split it in half reactions and then go from there. Okay, so you gotta remember either the oil rig or the Leo says GER. Oil rig, oops. Oxidation is losing, reduction is gaining. So look at this guy loses. It gets rid of electrons because they're on the product side. It lost them. It lost 2 of them. This guy, electrons are a reactant. It's taking them in. It is gaining electrons. So it is reduced. And then the agents are always just the opposite. So the reason that is because when this guy loses the electrons, it's because the permanganate is taking them. So it's actually causing this guy to be reduced. It's losing the electrons, but it's causing this guy to be reduced, which is why it's called the agent. And then permanganate takes in electrons, so it's reduced, but it's reduced by stealing cyanide's electrons. So it causes the cyanide to lose them, which makes it the oxidizing agent. It like facilitates that process. Does that help?
Okay, thank you. Yeah, for sure.
Okay. All right, so hopefully we could get here right. Now, what's next? So I have my half reactions all balanced. Now I need to force my electrons to balance. So what's coming between a 3 and a 2? Well, this is a pain. We have to do both of these, right? So you have to multiply the top one by 3 to get 6 electrons, and you multiply the bottom one by 2. So I'm going to rewrite out. So I'm going to end up with 3 waters plus 3 cyanides plus 3 CNO minus plus 6 hydrogen ions plus 6 electrons. The 3 gets distributed to everything in that top reaction, and then the 2 gets distributed to everything in this bottom reaction. So let's see, I have 6 electrons, 8 hydrogen ions, 2 permanganate ion, 2 manganese dioxide ion, or not ion, 4 waters. Okay, now, just like in any other problem, after we have all this out, we're going to cancel out things and subtract things that are similar on both sides. So I have 6 electrons on the left and 6 electrons on the right. So my 6 electrons go bye-bye. Now, I do have waters and hydrogen ions in common. So there's 8 hydrogen ions on the left right here and 6 on the right. So all 6 of these are gone, and 8 minus 6 leaves me with 2 hydrogen ions. Okay, I have 3 waters on the left and 4 waters on the right. So all 3 of these are gone, and I'm only left with 1 water over here. Okay, now, nothing I've done so far has been different than any of the other 3 problems that we did. So here's where the difference comes in for this being basic. Listen, listen, listen. If you have a basic solution, you cannot have hydrogen ion floating around in there. Hydrogen ion is what makes something acidic. So you do this whole problem just as if it were an acid, and then at the very end, you locate the hydrogen ions. They're right here. However many you have, that is how many hydroxide ions you are going to have. So if this said 10 hydrogen ions, you'd add 10 hydroxide ions. If this said 30 hydrogen ions, you'd add 30 hydroxide ions. It says 2 hydrogen ions, so I am going to add 2 hydroxide ions to the left side of this reaction. Well, just like in math, if I do that to the left side, I have to do that to the right side also. So I have to put 2 hydroxide ions on the right side of the arrow also. Now this is where it gets tricky. What do H plus and OH minus make?
Water.
Water. Good. So what's happening right here is pretty much neutralization. So if I have 2 H's and 2 OH's, these are really going to combine to make 2 waters. So you have to go back and re-reduce the waters because there's a water over here. So there's one water on the right and now there's two on the left. So I have to re-reduce my water. So this water is gone and 2 minus 1 is 1. So now I just have one water left over. So I added the hydroxides to both sides. This neutralized the hydrogen ion. So now you see at the end, you don't have hydrogen ion floating around in there. You have hydroxide ion, which is what makes something basic right now for the sake of this class. So, write out what we have. Let's see, what do we have? We have a water, H2O. On the left side, we have 3 cyanides. On the left side, we have 2 permanganates on the left side. That's it for the left side. The right side has 3 CNO minuses. It has 2 manganese dioxide, MnO2. And don't forget the 2 hydroxides. This is what now makes my solution basic. There's no H plus ions anymore. They've been neutralized and turned into water, and there's excess hydroxide. This is what is making it basic. So again, the problem is identical to an acid problem until the very end where you introduce hydroxide ions. So that is all I have for you today. I'm happy to hang around and answer questions or go back over some of the problems if you'd like. But this is pretty much the end of the notes in terms of content. You know how to do all types of redox problems now. So I'm mostly done teaching content. I'll still finish the notes, but we don't have anything new after this for chapter 4.